John, are you there? Oh, can you hear us, John? Deafening silence is a bad start. John, can you hear us okay? This isn't good, is it?
Can you,
Oh.
I'm going to turn off my video because I don't want to jam the internet.
Okay, well, we can hear you now, which is a good start.
Okay, cool. I'm going to, let me see if I can get my screen to show up.
Okay.
Let's see.
I think, can you see us on this end?
Yes.
Great. That's a good start.
It's great to be able to do this electronically.
Yeah. You never quite know how it's going to work. Can you guys all hear him okay? You can all hear him.
Can you see my screen yet? I got to figure out how to do this screen share.
Okay, we don't have it yet, no.
Okay. I'm not very facile with this.
You're as bad as me, probably, just. I don't know what it looks like in yours, but there's a little button down the bottom right corner which gives you the option of sharing a screen.
So I'm trying to figure out how to share my screen yet, which is, let's see.
Proving elusive, is it? I'm not sure what you can see in yours, but do you have a couple of icons down in the bottom right-hand side of your screen?
Yes. Oh, yeah, here it is. Okay.
Oh, there we go. So they can see themselves at the moment.
Okay, did that work?
Yeah, so we've got your screen, but obviously you've got the video of us in the middle of your screen at the moment, I guess. So I might need to minimize that a bit.
And I'm going to send you the talk. It's a PDF because I can't. The talk itself is pretty big.
Yeah, no problem. I'll be able to put that online.
So the bottom line is that we don't have to. You guys don't have to. Take notes if you don't want to.
Okay. Are you able to minimize the video of us that you've got in the middle of your screen?
Okay.
There we go. Now we can see everything. That's great.
All right. I keep getting all these stupid pop-ups. Sorry.
Yeah. Yes, we're watching them all fly in.
Actually, what I'm going to do is turn off my email because that seems to be the source of problems.
Yeah.
Okay, how does that look?
I think that's great. Yeah. So, yeah.
Okay, cool. So we have till when?
As long as we're done by 5 o'clock at the very latest.
So that's 2 hours?
2 hours at the very latest. Yeah.
Okay, cool. All right, well, let's get going here. So the talk I'm going to be giving today is going to cover crew survivability with a heavy focus on crew escape, and I'll talk about those terms, in just a little bit. Just by way of introduction, I was a naval flight officer, bombardier navigator. I was also a Special Forces freefall parachutist and a Navy flight surgeon and Navy diver. So I had a very broad background. Before I went to NASA, I was at NASA 8 years as a shuttle crew surgeon, and my last period there, I was basically on the crew survival investigation team that was about a 3-year program of investigating the Columbia accident after the initial Columbia accident board report was done. I left NASA, went to academia at the Baylor College of Medicine and at the Center for Space Medicine. But during that time, I also had the opportunity to do a number of other programs. So as a result of that, I ended up only working there part-time because I was working on the Red Bull Stratus. And then as soon as that was done, which was 2012, I was on a second stratospheric freefall parachute program called Stratex Space Dive. So and I'm still working on other high altitude escape projects. So it's something that's near and dear to my heart. So what we're going to do is I'll just go through some of the initial objectives for this lesson. The basic ones are basically to understand the role of crew survivability plays in human exploration. Obviously, we want to keep crew alive and functioning, and for the most part, this involves challenges presented by off-nominal events that we'll talk about. If you all are interested, I can send you a YouTube link to my talk I do on space incidents and mishaps. So basically, that's all the ways you can die in space, and then this is about how you survive and live in space when a contingency happens. We'll talk, I'd say probably half the talk is going to be on crew escape, which is near and dear to my heart. And then we'll talk about survivability designs and how it's better to design a system up front for escape or survivability as opposed to trying to make a modification afterwards. For any human-rated system, and this includes aviation and space systems, and reality is it also applies to automobiles and other forms of transportation, that you basically have 4 different components that you're concerned with. Capability is, its range and payload and a number of people it can take and how long it can stay, in that environment aloft or in flight. Sustainability has to do with maintenance and basically the maintenance hour per flight hour, which is something that the companies often want to have an understanding of. And affordability has to do with the initial acquisition cost, and then the sustainment cost is buried in that as well. So affordability and sustainability are more about repeated operations. And then the final category is survivability. And you can notice in some vehicles, say for example, Land Rover, they pride themselves on their crashworthiness. So assuming you can't prevent an accident, how do you survive it? And one of the things that we'll talk about in a second is the difference between engineering that deals with safety and engineering that deals with survivability. So what is crew survival? Crew survival is basically the implementation of all those things that have to deal with a catastrophic or contingency situation. That can include abort, escape, egress, safe haven, and EMS and rescue are also involved in that, as eventually that be one of the things that is in the equation, because it's unlikely that you could take care of yourself after something like this for a long-term prospect. The bottom line is that crew survival is about options, and you'll see this, the idea of having options is always a good thing, but it comes at a cost. So our definitions that we just talked about, the difference between escape and egress. Egress essentially refers to getting out of the system on the either at launch or pre-takeoff or after landing, and getting to a safe, survivable location. Escape has to deal with getting the crew away from the vehicle in a catastrophic situation, and we'll talk about where it applies and doesn't apply. Abort is a generic term for any off-nominal situation, and we'll talk about the difference between an intact abort and a non-intact abort. And then rescue is the addition of supplemental personnel and systems to ensure crew safety. So it's interesting, if you look back even in the historic records, how important survival and escape systems were considered. And this is a series of articles that came out in a magazine called Collier's in the early 1950s. And Wernher von Braun, who was basically the reason we got to the moon, had written several of these articles, and I have those in my historic files if anybody wants them. But in one of the articles, this came out this was I think the third or fourth article, was talking about how man will conquer space, and the spacecraft that they were looking at was a winged vehicle. And shortly thereafter, they came out with a section on if the winged vehicle wasn't operational, how you could get out. And what you see there is these little pods that are jettisoned with little drogue parachutes. And this was the article that came out a year later, which went into detail of how will man meet emergencies in space travel. And by man, that was the time where, they considered everybody, men. Now we know that the more appropriate term would be how will humans meet emergencies in space travel. In the bottom left, you see a drawing there's a handwritten drawing in 1952 signed by Wernher von Braun of the escape pod that he envisioned, and then the artist's rendition of that in the Collier's magazine. And then here's an expanded version of it, which was basically a kind of neat idea, which was a telescopic encapsulated system. So it could be stowed in a configuration that would be a smaller volume and then deployed as necessary. Now, we'll talk a little bit about pros and cons of having to deploy a system before the contingency, because once something happens, very rapidly it can deteriorate, and you may not have time to get in this specific pod shown here. But the novel thing about it was that it included a lot of the different considerations, such as a life support system and a pressure vessel to protect the crew from the surrounding adverse atmosphere. But we'll step back to actually what was arguably the very first space race. And that was in the 1930s, and it involved stratospheric balloons that were ascending to altitudes previously never attained by humans. And I like to show these. These were two covers of magazines in the mid-30s that portrayed some of the issues, but they also included an escape system. As you can see on the left, you see this parachute attached to the seat pan. And the irony of it is that this drawing is almost identical to the system that was used by the Stratic space dive, which was a balloon carrying a spacesuited passenger to altitude with a parachute decelerator. So let's talk a little bit about that early space race. This was in early 30s, and the Russians, who had a long interest in high altitude activities, including stratospheric balloons and parachuting, had developed a balloon system that got to 72,000 feet or 22 kilometers, which is, for its time, amazing. The problem is that these balloons were made out of rubberized canvas, and that's not a very good material in extreme cold temperatures, which certainly the stratosphere can get into the minus 60, 70, 80 degrees Celsius. So the balloon ruptured at its float altitude, and it started to descend, and the crew had a bailout system intended, but if you look at this hatch, you can see that there were some potential issues with that. One is that there were lots of different screws that had to be undone, little wing nuts. So when the balloon ruptured and it started to descend and tumble, the crew were unable to get the hatch open. and so they were unable to implement their bailout system. At around the same time, the U.S. had a similar program called Explorer, and it was a program between the Army Air Corps and the National Geographic, and this was their first attempt, Explorer 1, which ascended to 64,000 feet, which is right around Armstrong's line, and it also ruptured. But the difference is that the crew were able to get their hatch open quickly and get their parachutes on and bail out. But it took them quite a while to do that, and as you can see, this was a shot of the original balloon rupture, which actually forms a parachute decelerator system. But as it got lower and lower, it eventually broke, the balloon itself broke apart, and so the capsule started tumbling and coming down a lot faster. You can see here, one of the first parachutists to get out was the junior guy, Anderson, and he bailed out at about 4,000 feet. And then you can see as the balloon is deteriorating, buried in here are two parachutes. One is at the very top, that was Stevens, and then the senior guy was the last to leave the ship, and he got out at below 1,000 feet just before the balloon impact occurred. You can see it right there, seconds later as it impacts a field. His parachute is fully inflated. So these crews both sustained catastrophic failure of their vehicle system, the balloon. One group died because they couldn't get out of their vehicle. The second group survived because they could. So escape systems have to consider all different variables, including getting the hatch open. So the second big race to space prior to the actual rockets going up and carrying crew was in the late 50s and early 60s. And it was also a race between the U.S. and the Soviet Union. Here's two pictures of covers of books. One's called Touching Space, which was about the Project Manhigh, and the other was about, it's about the astronauts or pre-astronauts, as Craig Ryan wrote about them, which was basically ballooning at the threshold of space. Much of the early space program benefited immensely from these balloon stratospheric test programs. Now, in the U.S., both the U.S. Navy and the U.S. Air Force had programs. I'll talk mostly about the Air Force program, but both of them were very, very successful. This was a picture of Project Manhigh, which flew 3 times to the stratosphere and exceeded 100,000 feet, and on the final flights, 2 flights, they were over a day in length. This middle picture is the picture of the last of the Air Force programs called, this was called Stargazer, and it was a stratospheric atmospheric astronomy program. And then the final program the Air Force had was called Excelsior, which was an actual planned jump from the high altitude of the stratosphere. And for the purposes of space, they considered space anything over Armstrong's line, which was 63,000 feet. Joe Kittinger did 3 jumps from the stratosphere. Each jump had its lessons learned, and actually on 2 jumps there were near catastrophic issues. The first jump resulted in a flat spin where he went unconscious, passed out, and his reserve parachute had a timer, and so it opened and saved him. And on his third jump, which is shown here, he actually lost glove pressure in his right hand, and his hand swelled up in the vacuum of space and basically plucked the glove leak off. At around the same time, the Russian or Soviet Union was conducting a high-altitude balloon parachute jump program, which was called Volga, which is named after a river in Russia. The Volga capsule was actually it was a modified Vostok capsule, so it was the exact same capsule configuration that Yuri Gagarin was using. The difference was that they used, the first jumper that jumped out of it used an ejection seat, and the jumper behind him used just a manual bailout. So we'll talk a little bit about this because it's a fascinating program. The two test parachutists were Air Force officers, Yevgeny Andreev on the left and Peter Dolgoff on the right. And both of them were very experienced test parachutists with many thousands of jumps. They were testing high altitude bailout, including ejection seat and also a manual bailout. Andreev went out first in using a propulsive ejection seat. In other words, not a rocket seat, because that would have burned the remaining parachutist Dolgoff. And he set a world record of 83,000 feet from his jump. Unfortunately, Peter Dolgoff, who came out after him, or bailed out after him, did a manual bailout. And the problem is, this is kind of a grainy picture, but what you see is you see the pressure suit, which was a Air Force high altitude pressure suit, and it uses a plexiglass fishbowl type helmet, which gives you a great visibility. But you can imagine one thing it doesn't do is it gives you plexiglass is potentially shatterable. And sure enough, as he went out, he clipped the back of his. So here's a picture of him in practice doing the bailout, but you can see this rim there, and you've got to get out in a bulky pressure suit, which is inflated, obviously, because you're at very high altitudes, 83,000, or he was at 86,000 feet, so his suit is very bulky, and most of the Russian suits were pressurized to over 5 psi, or a third of an atmosphere, so they're quite limited in their dexterity. But what happened is, he snagged himself going out of the edge. He was sitting down and then basically trying to roll forward, and because of the bulk of his parachute, his helmet hit. And here's a picture of the hole in his helmet, which is about the size of your thumb. Now, he could have potentially survived if the parachute, if he had free fall to a lower altitude. But this jump was intended to do a high altitude, high opening. So his parachute opened in the 80,000 foot range, and so he's descending at about 1,000 feet per minute. So quite literally, he was exposed to the vacuum of space for probably at least 15 to 20 minutes before he got below Armstrong's line. He perished and was buried in the Kremlin wall in a very full military honor. But he was one of the early casualties of the space race. So in the mid-1960s, a civilian parachutist named Nick Piananta, who Craig Ryan also wrote about in this book, Magnificent Failure, borrowed a suit from the David Clark Company and had his balloon program funded. He did three ascents in a balloon. Each time he had issues and didn't succeed, including he got to 123,000 feet on his second balloon ascent, but he couldn't disconnect from the life support system in the gondola. And on his third jump, as he was ascending at about 60,000 feet, here you can see the gondola. It's an open style gondola. His visor inadvertently opened, and as a result of that, he rapidly lost consciousness. He couldn't get the visor down, and there's a whole interest in why did the visor open. The suspicions are either he opened it to burp the moisture, or he pushed the wrong visor. And I'll just point out that this helmet, can you see my little arrow? So on the screen there's two buttons that open the visors. The right button opened the sun visor, and the left side had a similar button that opened the pressure visor. And there's thoughts that he pushed the wrong side and it opened, or he was bouncing around inside and his head bumped at the pressure visor opened. Anyway, the bottom line is the visor opened at a high altitude. This is actually a picture taken by a crew recovery aircraft that circled him, and he's slumped over in his gondola, and his emergency parachute is opened but he's still stuck in this descent parachute, which is coming down very slowly. Anyway, he didn't die right away, but he died 4 months later from essentially anoxic brain damage. And here's a picture from the paper of that. This was his surgeon, a flight surgeon, Len Thompson, who I had the honor of meeting and talking to him at length about that mission. So, as a result of the high altitude parachute program the Air Force conducted in 1959 and 1960, Project Mercury, which was the first U.S. Human spaceflight effort, put a emergency personal parachute system in their first two launches, which was called Mercury Redstone. Now, there was Mercury Redstone and Mercury Atlas. Mercury Redstone was a suborbital flight, and the crew wanted to have a backup system to the capsule parachute, so they put in an emergency bailout parachute for those two flights. Here you see Alan Shepard, who flew a Mercury Redstone 3, in 1961. It was a suborbital flight, so he was only up for about 15 minutes. But you see, he had an emergency bailout parachute in case the capsule parachute system failed. After the two flights of Mercury Redstone, they had confidence in the capsule parachute, so they took this system and no longer used it. So let's talk a little bit about the atmosphere of space and what we face. If you look at an atmosphere, this is a view of a sunrise, and you actually can see these layers of the atmosphere. This is a kind of not as clear a photo as I've seen, but basically that you can actually see the layers of the atmosphere. And as a point of reference, it would be like 3 sheets of paper on a soccer ball. And if you divide the space, is considered 100 kilometers. In other words, to get to space, you have to go to 62 miles or 100 kilometers, which is about 330,000 feet. So essentially, those 3 sheets of paper equate to about 33 kilometers, or about 150,000 feet. So if you look at this, the first sheet of paper is where you see the troposphere and the tropopause and the beginning of the stratosphere. And we fly vehicles, when Concorde was flying, it was flying in the 50, 60,000 foot range. The Gulfstream 5 can fly above 50,000 feet. So we have aircraft that can fly in the stratosphere. I'll talk a little bit later about the jump programs, but all the first jump to go to 100,000 feet was, about in this range here, in the low stratosphere. The final jump, Alan Eustace's jump, and Felix Baumgartner. Felix was at 38 kilometers, and Alan was at 41 kilometers. So we've seen people actually do free falls up to, up through that first sheet and a half of paper. But we have very little experience of what happens in these upper regions of the atmosphere, the mesosphere. We do know in the stratosphere you've got molecular oxygen, or ozone, which you have to make material that's going to be tolerant to that very reactive compound. And we'll talk a little bit about some of the other threats as you go higher and higher. So not only do you face extremely low temperatures, but you also face very low pressures, and then other things. Essentially, by that first sheet of paper, you are less than 1% of the atmosphere, and then by the time you get to the all 3 layers of the paper, you're essentially at 10,000th of a percent of atmosphere. So it's extremely intolerant of human survival. So now that we've seen that altitude chart, we'll look at some of the concerns we have in space flight risk. And essentially every one of these areas has a potential for catastrophic failures. For the purposes of illustration, There's actually a chart that goes through, and if you're interested in more detail, I can send you this chart. But it's a chart that NASA updates with all of the events that have happened in space and that have killed people and have injured people, or just that have happened, so you get a historic perspective. The launch pad is very dangerous because of its, you've got chemical energy stored, you've got cryogenic material, you've got at launch you've got exceptionally high acoustic loads and vibration loads. And we've lost crew in the launch phase. That was Apollo 1, which was just a test flight that had a combustion event in a pressurized vessel with 100% oxygen. All the other fatalities that have occurred either on launch or reentry and landing. And that's where you're having major transitions of energy states from chemical energy to kinetic and potential energy, and then on reentry, you're turning potential and kinetic energy into thermal energy to dissipate. But what it shows you is that if we want to cover the entire mission, we have to cover all of these phases, including the pre-ingress phase and waiting on the launch pad for the launch window to open, the ascent phase where you're going through the speed of sound and you're accelerating extremely rapidly. We also, especially now that we're on ISS, you spend a lot of time here, and because you spend a lot of time on orbit, you've got more of a window of potential events to happen. And then finally, you've got deorbit, reentry, and landing. So each system will have things that we will address the different survival modalities here. So this was a chart I broke down that concerns all of the health threats for ascent and entry, which are the primary threat matrices that we deal with for escape systems. You've got molecular oxygen, in the ozone, which also can be exceptionally high temperature, in the 3,000 degrees centigrade range. G-forces, shock-shock interaction refers to especially vehicles that are going faster than Mach 1, that as a vehicle breaks up, it can create differential shock waves that can cause shearing. This was a component of Columbia's survival investigation that previously had identified, or that had not previously had this issue, but it came up as clearly a injury potential for crew. You've got dynamic heating and dynamic pressure, and then you've got the different atmospheric conditions that can cause health effects. I'll talk a little bit more about ebulism in detail, but basically exposure to any atmosphere that's higher than the boiling, vapor pressure of water can cause ebulism. If you have a depressurization above anything greater than half an atmosphere, reduction in pressure, you can get evolved gas or nitrogen bubbles coming out, which is called decompression sickness. If you have a pressure differential exceeding 70 millimeters of mercury per second, you can have barotrauma, the most significant of which is pulmonary overinflation syndrome resulting in cerebral arterial gas embolism. And then finally, if you have a oxygen partial pressure of less than 180 millimeters of mercury, you can sustain cognitive loss from hypoxia. Terrain impact and intrusion of habitable space can occur. And these are things that are also of concern in aircraft and also motor vehicles. The countermeasures are listed over on the far right, and they include a number of different things to protect the crew from these reentry and ascent threat. So what I did was I took all of the cases that we could garner information from, and plot them out on a flight envelope. A typical flight envelope is airspeed on the x-axis down on the bottom, and on the y-axis we have altitude in thousands of feet. So the very top of this is 150,000 feet. So what you see here as the blue line would be what the shuttle reentry profile was like, and the red line is the ascent profile. So what you can see there is what you see there are two lines that would be a typical winged vehicle reentry. And what I plotted here in the fatality envelope, these were the two parachute jumps that had fatalities at they were at zero airspeed because they were in a balloon, but this was at 86,000 feet and this was at 58,000 feet. That was a strata jump with Nick Pianata and Peter Dolgov on the Volga balloon jump. Both of those were in the 1960s. We can see the Challenger mishap occurred at around Mach 2 and about above 50,000 feet, and it lofted. All 7 crew members, they were not wearing any protective ensemble. They did not have a pressure suit on or even oxygen available. We also have 2 SR-71s that broke up at 78,000 feet going Mach 3.2. And amazingly, we had crew that survived those. So these were two crew vehicles, and we lost 1 crew from a broken neck. And then one died afterwards in drowning. But they both, the 3 out of 4 survived the break at Mach 3.2 and about 80,000 feet. What's interesting to note here on this far right, these lines here, these are ISO lines for ballistic coefficient measured in pounds per square foot and also in knots equivalent airspeed. And so what you see here is, you know, this gives you a good indication of the dynamic pressures that they were encountering. And you can see here that, as we'll talk a little bit about later, the fatality envelope really starts when you get up above about 600 knots equivalent airspeed and above 1,000 pounds per square foot. Those are where you really see very high fatalities. This is an interesting one. In 2014, end of October 2014, Spaceship Two, as part of Scale Composites' final flight test on powered Flight 4 broke apart. There's a whole human factors issue there I won't talk about, but 1 crew member died and 1 survived. So here you see the survival flight envelope, and if you just go back and forth, what you see there is we're not in a 100% fatality envelope. We're in maybe a 50% fatality envelope where you see some live and some die. These were the 3 jumps. This was Joe Kittinger in 1960, who was just shy of Mach 1, and then both Red Bull Stratus and Stratic Space Dive exceeded Mach 1.2. Like I said, 3 of the 4 SR-71 crew members survived the initial breakup, although one of these guys drowned after landing in the water, very close, similar to what Gus Grissom had. So what we're seeing here is, you know, an idea of who lives, who dies, and then these were chamber accidents, vacuum chamber accidents where crew members survived. And here was an interesting one. This occurred in the 1980s, an industrial chamber accident, 74,000 feet for 3 minutes. So he was above Armstrong's line for quite a few minutes. He was unconscious and very bad off, but he survived and completely recovered. And then these were 2 vacuum chamber exposures in excess of 100,000 feet. So what happens at altitude? Every time we would take a crew member up in a vacuum chamber, they would carry a flask of water, and you could see this flask of water just literally turning from a liquid to a gas, going, effervescing like a soda can popped. And what happens is our body's made up of 70% water, so water inside your body exposed to vacuum also goes through a similar process, which is basically water vapor bubbles. And this is a very serious problem. Now, you see this crew member is wearing a pressure suit from the 50s and 60s called a partial pressure suit, or a capstan suit. We now use full pressure suits, although the shuttle in the early years used a partial pressure suit. What happens to the lung tissue is what's primarily the thing that causes the fatality. You see a normal lung with 2-cell alveoli here and vascular structures to exchange oxygen to the blood. And here's an ebulism lung. This is actual human tissue from the Columbia mishap. You see a massive disruption of the pulmonary alveoli. So ebulism is the term for exposure to tissue above water vapor pressure, which occurs at, if you remember your pulmonary gas equation, 47 millimeters of mercury. And that's equivalent to about 63,000 feet. But I would add that it's not a specific demarcation, because we can see it even below that altitude, maybe even as low as 55,000 feet. What happens is you get water vapor in the blood vessels that causes essentially a vapor lock in the cardiovascular system, and then you blow these water vapor bubbles into the brain, and you can have embolic phenomena. But recently, we've been very concerned about this issue, but what we've also found is that there's a higher altitude than Armstrong's line that also creates an area of concern, and that's the triple point of water. And at the triple point of water and physical chemical principles, you can have all three states of matter existing simultaneously. They can be a liquid, a gas, and a solid. And I'm going to show you a video of that transition to the triple point, which may actually be a far worse thing than just ebulism alone. Take a look at this video.
There we go. Right now, look at me.
Holy shit.
There's a tray of water there, and it looks like the video is kind of stuttering. But what you're seeing is at about 113,000 feet, water is liquid, a solid, and a gas all at the same time. And afterwards, we bring it back down and eat it, and it's called space ice. Okay, so what are the things that we worry about in crew survivability? One is, what's the coverage range? Well, is it full envelope or partial envelope? What that means is that you cover the entire launch and ascent, orbital insertion, reentry, landing, or is it not? Is it not a full envelope? For example, the shuttle was only a partial envelope coverage. The other thing is we talk about intact or non-intact abort. And in an intact abort, the crew would come back in their vehicle, and in a non-intact abort, they would not come back in their vehicle. So basically, it's divided out into those systems that have capsules will generally go with an intact abort, and those systems that are wing vehicles will at least consider an option of a non-intact abort. The next category we look at is the protective systems that, and the big item there is, are they in a pressure suit or not? And there are pros and cons for each of those. And what we've realized is if you're going to spend any length of time above Armstrong's line, it's a good idea to consider wearing a pressure suit as a backup. But for suborbital vehicles, they're generally not going to do that because the time spent above Armstrong's line is really relatively small. And the pressure suits themselves add weight and complexity and heat. Heat buildup is a huge problem, especially because the transient from the launch phase to the microgravity phase and then the reentry phase is often accompanied by motion sickness. And there's no question that in a heated subject, they will be more motion sick. And then what are the systems that the crew have to do versus the automation involved? And then obviously post-landing support. So we'll talk a little bit more about these in detail as we get going. The operational coverage arena, in other words, you have to consider all these major phases. Launch and entry, or the launch pad and ground, which would be, you would do egress potentially, crew escape during launch and reentry, on-orbit opportunities such as a safe haven, the ability to transfer crew from one vehicle to a rescue vehicle, and then abort and return, and then finally post-landing survival, which I won't talk much about, but obviously all the crews now that go to space train extensively in water and land survival. And there have been crews that have come back that have had to maintain, they have not been recovered, including several days later. That was early in the Soyuz program. Launchpad has got a huge number of threats. We won't go into all these, but obviously these are things of major concern. And as a result of that, the idea is that in a launch pad catastrophic situation, you would strongly consider a launch abort system, a launch escape system to get you out of this condition. And I'll just talk about some of the, first thing is to get away from the vehicle before systems catastrophically failed. And I'll show you some representative examples that have been used. Mercury had, this is Mercury Redstone, this is the suborbital rocket, but it had a very, immature system, which is basically a cherry picker. And you'll see as these systems evolved over time. Apollo had multiple launch escape systems, including a elevator, a slide basket, and they had a unique one, which was a Teflon tube that went from the crew ingress area. You would slide down this tube and it would make a 90-degree turn, and you'd end up in this bunker that would be able to keep you alive for 24 hours. It would also be able to keep the closeout crew alive too. That's still, that chamber is still present under the Launch Complex 39A and B. For the shuttle, they could take the elevator or they could use a slide wire basket. Here's crew would train on terminal countdown test. There were 7 of these baskets, and you could put 3 crew members in each basket and also the closeout crew. And then they would slide down wires about a half a mile away to a bunker where they could reside, or they could get in an armored personnel carrier and drive further away. For the Constellation and also for Orion, they're looking at the huge advances have been made in the industry in entertainment rides, and so they've gone with the concept where they would use these trolleys that could go very fast. Problem is the slide wire system is a lot slower than this trolley system. Would be quite a ride. The 2 commercial launch providers for NASA are Boeing Starliner and the SpaceX Crew Dragon, and both of those are going to use slide wire systems, as you can see here. This is the Boeing launch pad that's is under construction at Kennedy Space Center, and you can see now for these folks, they're going to use individual slide descent systems. And in fact, this is very close to what this is where the shuttle baskets ended up going to. That, see where that green box is? That's where the shuttle system was. So these slide wire systems go about half again as far. For SpaceX, they're using the 7 slide wire systems that NASA had set up, and they actually refurbished Launch Complex 39A. So the other thing I talked about was once you're in the vehicle and you have a failure during the early ascent or launch phase, you use a launch escape system. The purpose of which is to pull the capsule away from the catastrophic environment. But you also have to provide parameters, and I'll show you some of the launch tests that have been done. You have to survive the acceleration off the launch pad and reorient the vehicle so that the parachutes can come out and not tangle. These systems have been tested. Even the Mercury had a launch escape system, as you can see tested here. This was tested 6 times at Wallops Island, Virginia. And if you go to Johnson Space Center, you'll see this. This is the Little Joe 2 launch system that is shown here at White Sands, New Mexico, and it did 4 launch ascent tests prior to the human cruise. The Soyuz launch escape system is quite robust, and it was actually tested right after a modification as recently as Soyuz MS-10, which was earlier last year. This is actually launched off the pad and had several ascent breakups as well. Soyuz T-10 had a launch pad aboard, and the 18A and the MS-10. The Orion is the NASA spacecraft designed to go to Gateway and to lunar and other, deep space missions. And it has this system you can see here. It's got the a tractor motor which pulls it off with an aeroshell to protect the capsule. This system, the tractor ascent system, is used in early ascent aborts, and then this system is jettisoned, and then it still has a pusher motor that can be used for downstream aborts. And you can see this broken out. The ascent systems are broken out by different modes that have to do with the early ascent phase, which is this outer shell, and then the pusher system, which is for further on down. It can even have the ability to abort to orbit. Here's some tests.
2, 1, launch.
Flight test of Orion's launch abort
That's
system.
a launch
The
pad.
test, performed in New Mexico and simulated using Lockheed Martin investment hardware and software, was 100% successful. The abort system worked flawlessly as its 500,000 pounds of thrust propelled the test spacecraft a mile up and a mile away from danger, allowing it to parachute safely back to Earth.
There you see the parachute one. Actually landed in Mexico. This was a test of an ascent abort motor. So this would be during. This was actually a test done with the pusher motor. So the previous one was the tractor rocket that pulled it off, and then this is the pusher motor test. And you can see it. Here's a video of it being tested. So having 2 different systems are useful during different phases of flight. And then they wanted to test the parachute system. So you see the shroud come off and separate. That's the ring that separates, and you'll see the parachute. These are drogue parachutes that separate the aeroshell, and then you'll see the capsule come out with the pilot chutes that separate the motor. So there's been a huge amount of testing that's done in these systems because they absolutely have to work. So here you'll see that. So there's the aeroshell separated. Those are the pilot chutes that'll pull out the main parachute deployment bags. In just a second. There's the deployment bag. And all of these 3 chutes, most of the systems now use 3 or 4 chutes. I'll talk a little bit about those. This is a recent test of the ascent abort system during dynamic pressure, which is when it's breaking through the speed of sound. And this is again a test of, so it launches and then the tractor motor pulls it off during this test. Crew Dragon's undergone extensive testing. This is the pusher system being tested, and then here you see numerous parachute tests. Normally the Crew Dragon uses 4 parachutes. Just a week ago, they did a parachute test where one of the parachutes intentionally failed, and it still came down at a very slow descent speed, usually landing about 28, 30 feet per second. Boeing Starliner just did a test a day after SpaceX, and they had an unintentional parachute failure. They have 3 parachutes. One of them failed, but the 2 parachutes that brought them down were still in a very survivable flow. So now let's talk about crew escape. Crew escape is really more pertinent to winged vehicles, although bailout was used for the Redstone or Mercury or Redstone series, and also all the Gemini used an ejection seat. We'll talk a little bit about each one of these. Bailout is where the crew themselves have to manually egress out of the vehicle. The problem with that is they have to be conscious to do that. This started after Challenger, which was the 25th shuttle mission in 1986. It broke apart, and this is the crew module which survived. And the crew was still alive, but they were unconscious because they didn't have an oxygen or pressure suit system. Here's a close-up view of that. This is the crew module. It's completely broken free. That's the nose cone. These are the front forward screens. The vehicle eventually attained a nose-down attitude because of the wires trailing out of it acted as a stabilization system. The crew had survived the breakup, but they were unconscious. They actually died with impact of the water. What's interesting is they had air packs in case there was smoke in the capsule or in the cockpit, and 3 out of the 4 recovered were activated. So that shows that some of the crew was still alive after the breakup. The bottom line is, after the Challenger mishap, of which there were a number of studies, it was determined that we should go back to a crew escape system. And there were a number of studies that were done looking at how do you escape from a space shuttle. We've gone through all these to garner information. So the shuttle had a crew escape system that was developed after the Challenger mishap to allow the crew the ability to get out of the vehicle. And there were 2 astronauts, Mike Foale, who's a former British guy, and Bill Shepard, who's the Navy SEAL. The problem with bailing out from the space shuttle in flight is this leading edge of the left wing. So if you would bail out and you didn't have a means to clear that left wing, you would impact either the leading edge or the Holmes pod. So the bottom line is they had to develop an escape pole, which you can see here, and this was a test done at China Lake in California. And they tested this pole, and these are actual test parachutists that jumped it. So the shuttle, after the Challenger mishap, developed an escape system that was either from controlled gliding flight, and here's the actual card, cue card that the astronauts would wear on their wrists as they were preparing for it. The other means was for a vehicle breakup where the wing was shed, and these 2 systems are trained extensively by astronauts flying the shuttle prior to launch. Here's a test of a pressure-suited subject undergoing a bailout from a aircraft using that system. After the Challenger mishap, the group initially were using the partial pressure suit called the launch escape suit, and so that was in place from '88 to the mid-'90s. And then they went to a full pressure suit, which was the advanced crew escape suit, from the mid-'90s till the end of the shuttle program in 2011. The ACES suit was certified to 100,000 feet and 600 knots, which is 1,000 pounds per square foot, which is a very significant airspeed and pressure. Just as a point of reference, Columbia breakup was at about 400 pounds per square foot in the about 180,000 feet, and the 2 SR-71 breakups were at also about 400 pounds per square foot. 3 out of 4 crew members survived those breakups. So the bottom line is the breakup of the Columbia was in a survivable range. There's still things that could have killed them, but if they had everything working right, they would have survived, or could have survived. We talk about 2 breakup scenarios. One is a low altitude breakup, and the other is a high altitude breakup. And I won't go through these in too much detail out of the interest of time, but they're in they'll be in your handouts, and you can write me if you have more interest. interesting thing that came out of the Michael Full and Bill Shepard report was that the crew have they can survive a breakup from an ascent much higher than they can survive a breakup on reentry, and that primarily has to do with potential and kinetic energy and thermal energy. But an ascent breakup, like happened on Columbia or on Challenger, that broke apart at about 50,000 feet, but it could have survived a breakup with the crew escape system up to just shy of 300,000 feet. The Columbia breakup was right around 180,000 feet, so it's potential that it could have survived. Interestingly enough, one of the things that we did was to train the crew in nose-down procedures. This is the forward fuselage trainer, which is used for ascent, which is pointy end up, and landing, which is pointy end forward. But we moved it upside down and had crew testing. This is Nick Patrick going through the initial stage testing of the getting out of the seat in a nose-down configuration. In a pressure suit with all the gear, this is no small feat. It's interesting that a bailout system was also present in Spaceship One. The pilot would deploy this red handle and the nose would fall off, and then they would just roll forward. Obviously, you couldn't do that if you had any airspeed, but if you were tumbling, it certainly would be a viable way to get out of the vehicle. And then Spaceship Two has a bailout system, which was what allowed one of the crew members, Pete Siebold, to survive the breakup of Spaceship Two. This was during powered flight right at transonic, right about Mach 0.92, and the vehicle the feathering system was armed, and it inadvertently went to the feathered position where the vehicle completely flipped backwards. So here you see this is the motor and the rocket in the direction of the velocity vector. The bottom line is that Pete Siebold was thrown free and his parachute automatically opened, and he was survived. The other crew member was still strapped in his seat, and he died on impact. We also know from the experience of the two supersonic stratospheric freefall test program that a greater than Mach 1.2, which is the definition of supersonic, is survivable in freefall. This was a capsule system, primarily life support, with a small bailout model, and this is almost identical to what the Space Shuttle Advanced Crew Escape Suit uses. As a result of the lessons learned from this program, NASA now has taken those modifications and called their suit the Modified Advanced Crew Escape Suit, or MESA suit. Alan Eustace used a suit that was very similar to a spacewalking EMU, self-contained life support system, and actually got about 8,000 feet higher than Felix. Ejection seats have been used extensively, actually since World War II. Several German aircraft had ejection seats, and I think there were 60 ejection seats that were fired in World War II. Ejection seats were adopted by the other militaries after World War II, especially in jet fighters. I think they're on the order of over 20,000 saves from ejection seats, and obviously one of the leaders there is the Martin Baker Company. Ejection seats have potential problems, though. One is if you eject at high speed, you can encounter wind blast and aerodynamic flail, which basically causes multiple extremity injuries and even fractures. You can also have the G-force from ejections, which can cause compression fractures in vertebral bodies. And then if you open a parachute too high at high altitude, you can have opening shock. Ejection seats have been used in spacecraft. The actual first U.S. spacecraft fatality was in 1967 with Major Mike Adams, who underwent a vehicle breakup after a loss of control. Unfortunately, he was not able to pull his ejection seat, and he perished on impact. Vostok, which was the Soviet first 6 flights that actually set the first orbital record, all used ejection seats for nominal reentry and nominal landing. The Russians did not trust their capsule parachute system, so they used an ejection seat, and all the crew were trained in this. Here's an ejection seat in a Russian museum, and all the crew used this ejection seat, including the first woman in space, Valentina Tereshkova, who flew on the 6th and last flight of Vostok series. Ejection seats were used in the Gemini capsule as a backup system to landing if the capsule parachute failed. It was also available for ascent. The shuttle had ejection seats in the Enterprise, which was their the landing. That was part of the landing tests that were used basically for final flight. So the approach and landing tests, or ALT flights, used an ejection seat, and the first 4 flights of Columbia had an ejection seat system similar to an Enterprise, which was the SR-71 seat and the SR-71 pressure suit. Here you see John Young and Robert Crippen in the shuttle trainer. The Russian Buran space shuttle, although it never flew manned, it only flew once unmanned, had a very robust ejection system, the K-36 seat, which is very similar to what's used in all their advanced fighters, and the Stritch pressure suit, which has been extensively tested. I'll make that available if anybody has any other questions. These are one of the things you have. These were actually ejected from Progress capsules on ascent to resupply space stations, and you can see the scorching of the visors from the reentry heat. So what you see here is a survival envelope for major injury threshold, which is the airspeed altitude component. And what you see is that the ascent profile for the shuttle borders the survivability envelope for the ejection seat. It improves as you get higher because the air density is lower. Here you see fatal injuries above 600 knots. It's right around the level where you start to see 100% fatal injuries. But you can see fatal injuries even down lower. We'll talk a little bit about that. So ejection seats were considered to be put back in the shuttle after the Columbia mishap. The problem is the analysis was it would be a huge weight penalty. And the other problem is if you used an ejection seat on ascent, look what would happen. You'd go into the main engine plume. So they actually developed a countermeasure to that, which was a Lexan Nextel fiber system that would keep you from burning up going through that very hot temperature regime. But ultimately, the ejection seats were rejected because of cost and weight, mostly the weight penalty. Extraction rockets have only been used in one aircraft that I know of, the A-1 Skyraider, which was a propeller-driven aircraft. But it was actually tested by NASA. This is a shuttle hatch out at Hurricane Mesa in Utah, and they tested mannequins using the extraction rocket. You can see that, first of all, this has a very small envelope which it can work, and the other problem is you have to carry active rockets inside the vehicle, so it was eventually rejected as well. Encapsulated seats have been used extensively in aviation. Here's a B-58 Hustler, which is a beautiful Delta Wing bomber, and it had encapsulated seats in it. You could actually still fly the vehicle with this seat, in the encapsulated configuration. It was tested up to Mach 2 and 70,000 feet. Modular systems are used also in both aviation and spacecraft with mixed results. The F-111B, the Aardvark, which is a fighter bomber, had an encapsulated seat to survive supersonic ejections. Problem is that landing weight for this is very high and very heavy. Here's a test of an encapsulated seat, and what you'll see is just prior to hitting, it has to deploy airbags, to cushion the shock load.
Engineers tackled the problem of crew survivability from a stricken plane in exactly the same way General Dynamics had with the F-111 crew capsule. But for the B-1, with a crew of 4, it would have to be much larger.
So you have huge airbags.
Would be great.
So this was a test of the B-1A encapsulated seat. There was one X-plane that had encapsulated seats, the X-2, and in 1956, Mel App got out of control, and he separated the module from the X2, but he couldn't get out of the module, and so he died on impact. So encapsulated seats have had a mixed track record. It was considered for the shuttle, but it had to have massive airbags, and basically the system would require pyrotechnics to separate the crew module, the massive parachutes and drogue chutes, and as a result of this, you couldn't put anything in the payload bay because you had to use counterweights to get the center of gravity back in a flyable configuration. I'll skip through this. This just compares escape systems with these different suits. Let's talk next about the on-orbit potential for crew survivability, and this would be in case the primary spacecraft was rendered uninhabitable, say for example from a toxic environment or loss of pressure. Now, right now, the on-orbit safe haven is the Soyuz. So if something happens on the ISS, they would have to go to the Soyuz, and that would be how they would survive until they could get home. Now, obviously, the Soyuz is their return vessel as well as their safe haven. It was interesting, a safe haven was actually used in Apollo 13. The lunar module was the safe haven for the crew until they got back in range where they could come back in their capsule. The problem is that it was, they had to retrofit the CO2 scrubbers because the system was incompatible. The lunar module was only intended for 48 to 72 hours with 2 crew members, and for the Apollo 13 mission, it had to have 3 crew members kept alive for 96 hours. But obviously it worked and it was successful. There was actually, during the return to flight phase of the shuttle, the first 2 flights that recertified the space shuttle, which flew several years after the Columbia mishap in 2003, used an abort to space station as their safe haven. It was called the Contingency Shuttle Crew Support, or CS squared. And what that would do is the crew would stay on board the space station until they could be rescued by another space shuttle. And that was called STS-300, which had a whole flight plan and mission profile that was in place for the first 2 return to flight missions. So they would go to the space station. If they couldn't bring the shuttle home, they would go to a safe haven mode for several months until they could launch a rescue shuttle. Obviously, when the shuttle was out of decommission in 2011, that no longer became an option. They also, and this was how they would bring the crew back, they would have been deconditioned on the space station, so they would have to lie recumbent, strapped to the floor. They would launch with 4 crew on the flight deck, and all of the astronauts they'd bring back on the mid deck, the safe haven astronaut. I'll talk a little bit about crew transfer, because that was another potential area where you would send a rescue vehicle up and then you would have to get from one vehicle to another. These are some novel concepts that have been designed. The bottom one here, called the personal rescue sphere, personal rescue enclosure, was actually built, tested. Here you see, here's a mock-up of it in the neutral buoyancy lab with the 2 rescue spheres and a spacesuit. And astronauts in the early selection process until recently actually had to go in this thing for, I think, an hour, and that was a claustrophobia test. Here are the first women astronauts showing the rescue sphere. It was made out of Kevlar. it was able to provide life support for 1 hour. It was pretty small. And basically, if you can survive the claustrophobic environment, that was one of the criteria for being an astronaut. Here it's being tested in a vacuum chamber. And there was one other Skylab rescue mission plan, or one other rescue mission plan, which used, this was for Skylab 4. The command module was felt to be potentially not able to do re-entry. So the plan was to launch a rescue mission, which would have 2 astronauts launch and then bring back 3 crew members who would be deconditioned. The way they had to do it is they had to put 2 crew members underneath the pallet, which would have been a real challenge, but it was apparently tested and was certified for flight. Fortunately, the Skylab 4 crew module was managed to be fixed to the point where it could do a re-entry. Intervehicular crew transfers were considered for a rescue mission to the Columbia mission as part of the analysis after the Columbia accident. This would have been very challenging because there was no robotic arm on the Columbia, so that they would have to do station keeping and do a tether line transfer. The rescue, a shuttle-to-shuttle rescue was revived when they decided to go back to the Hubble mission, which was STS-25, and they had a standby shuttle, which was Endeavour, on the pad at the same time. They had a 4 crew trained, and they would bring back all 7 of the Hubble crew. So here's Atlantis getting ready to launch for the Hubble repair, and then the rescue shuttle on the pad ready to go with the crew. They were on standby, but they were ready to go within a couple of days to launch to rescue them. Obviously, that never happened. They would use their robotic arms to station keep and transfer crew members. We'll talk a little bit about crew return. There are a lot of different things you have to endure on re-entry. And this is to point out re-entry issues you face. There are deceleration limits. Obviously, if you come straight down with a ballistic, with a lifted drag of 1, that's essentially a ballistic re-entry. And we do bring back certain spacecraft in that mode for emergencies, like the Soyuz. You have to undergo concerns about heating, and then a big problem is where do you land so you can have crew recovery forces there to get you. So the bottom line is there's this, for any re-entry, whether it's a nominal or off-nominal re-entry, you have all of these different constraints. You have a G limits constraint, you have dynamic pressure limits. If you come in too shallow, you can bounce off the atmosphere and go back out into space. That obviously wouldn't be good. And then you have different re-entry heating limits. So essentially, a re-entry vessel or vehicle, particularly in an off-nominal situation, has to thread the needle in this process. I'll talk about 2 different vehicle designs and the pros and cons of each of those. You have blunt capsule such as the Soyuz, Apollo, and you have winged or vehicles that have the ability to go cross range, either because of their shape and their aerodynamic surfaces. So there's 2 major considerations that have to do with the difference between a winged vehicle and a blunt capsule. A blunt capsule is going to come down with less lift to drag. A typical capsule like the Soyuz has a lift to drag ratio of about 0.25 or 0.2. So it's down here in the bottom left corner. What does that mean? On the y-axis, you see what's called cross range, which is the ability to go side to side on that reentry corridor. As you get higher lift to drag vehicles, the shuttle was a lift to drag vehicle of about 3, which is still not very good. Gliders, really high performance gliders have lift to drag ratios at about 50. But what a lift to drag ratio of about 3 gives you is about 1,500 miles across range. Now, what does that mean? That means that if you launch and you do an abort once around, you can actually land at the same place you took off from. A capsule could not do that. It has a cross range that's only a couple hundred kilometers. So it cannot do an abort once around, whereas a winged vehicle can. Now, so we talk about you say, well, why won't you just always have high lift to drag vehicles? The downside is their volumetric efficiency is greatly reduced. And that means that you can carry less payload for the size of your spacecraft. So in this graph, this is the lift to drag versus volumetric efficiency. High capsules have very, very high or very good lift volumetric efficiency, but very low lift to drag. So that's the downside of a winged vehicle, is it has reduced volumetric efficiencies. I'll talk a little bit about reentry systems here. One of the things that's really super hot now is inflatable systems. What does an inflatable system do? It gives you higher cross-sectional area, but you don't deploy with a high cross-sectional area. So you can launch in a compact configuration and re-enter with a higher cross-sectional area. And these systems have been tested extensively, even in the early space programs. Here's the thing called fabric inflatable reentry structure test. And here's the concept. Crew would come back, or payload could come back in a pod like this, or the human pod actually was in the axis of the midline, so it would be a very tolerable G-force reentry. It was tested with a payload, and this was in the 60s. Unfortunately, one of these sides deflated slightly, so it came in a kind of a spiraling pattern, almost like a maple leaf seed coming down. There was a number of other systems that were conceptually designed. The Moose system, man out of space easiest, then changed to manned orbital operations safety equipment. And then Paracone was another one that was tested. But these things relied on reentry systems that would dissipate the heat and protect the crew from all those elements that we showed in that previous chart. But aerodynamic decelerators are super hot now, particularly in Mars exploration. Moon doesn't have an atmosphere, so an aerodynamic decelerator isn't going to work, but Mars does. Even though it's about 1% of the Earth's atmosphere, you're coming in at the reentry speeds necessary. A small decelerator can still get a lot of aerodynamic drag from these. So these have been heavily tested. And there's a concept, this is by a company called MPO Levuchkin, that has an aerodynamic inflatable decelerator bailout system designed for spacecraft. And here you see one coming off the ISS. These are actually, you can see here's a Sokol-suited crew member, and this is a test article where they dropped it off of a drop tower. These are also potentially useful for bailing out from buildings. So here's an aerodynamic decelerator that was tested. There were quite a number of these programs. There was IRVI, Inflatable Reentry Vehicle Experiment, which is a US, IDART, which is the ESA-1 Inflatable Reentry Demonstration Test. So here's the stowed configuration, and then here's the deployed configuration. And what you see here is, and right now we're actively exploring crew reentry systems that would need about a 4-meter reentry cone. Here's the problem I see, and this is from one of the test missions. And what you'll see is you'd be supposedly lying on your back, and if you're deconditioned from microgravity for several months, you're going to be very motion susceptible. So you have this kind of burble that happens as it captures the atmosphere, kind of rocking. And then as you get down lower, you actually start to spin. So you're coming in, but you still have this kind of burble effect. So there's the writing's still on the wall as to whether this is going to be viable for a deconditioned or incapacitated crew member. Here's the system that's used most commonly right now for reentry of crew. It's the Sokol KV-2 launch and entry suit. It is not considered an escape suit because it has no ability to survive outside of the spacecraft because it's not thermally protected. So it's a launch and entry or survival suit. But you can stay inside this as a safe haven on the space station for up to 30 hours. It's pretty lightweight. It's about 10 pounds. 10 kilograms. The Stritch suit was about twice that weight. And we've extensively tested it here at our labs. After you've re-entered the atmosphere, you have to survive the impact with Earth. Now, this is not a fire. This is the braking rockets that are firing right as the vehicle, the Soyuz spacecraft, is about to meter off the ground. Those braking rockets slow the vehicle down to a far less, high impact. But everybody that I've talked to said it's still like a pretty bad rear-end car crash. Here are the braking rockets that are been expended. Interestingly enough, they use a cesium emitter, and once the detector gets the reflection from the soil, it fires the braking rockets. So some poor guy has to come out and put this cover on the cesium emitter. Like many seats, they have a shock-absorbing stroking seat mechanism, and this one is about 25 centimeters, or a 25 centimeter stroke. So it allows that once the impact occurs, this allows the further deceleration inside the capsule. The Orion seats are going to be have a lot more restraint system. They'll have a 5-point restraint with extremity tethers and lower extremity tethers. Now, this is an interesting concept. If you notice here, what this uses is an extending stroke. So the previous ones were compressive strokes, and this is an extending stroke. And here's some of the modeling that shows that extension system as impact with water occurs. And then I would add that you're not home until you're sitting home on your couch. Once you land somewhere, even on planet Earth, you might be in the water, you might be on a remote island, you might be in a desert or an ice floe. So all crews are trained extensively on survival post-landing. These are some reference material. I have several of these electronically. If you're interested in, I can provide you links to those. These are 2 books that came out. This one came out in 2008, Columbia Survival Investigation Report, and Loss of Signal came out in 2014, and it goes through a very extensive aeromedical analysis of injuries and crew survival lessons learned. This is a great book on spacesuits that's also available electronically. It's also a nice coffee table book if you want to buy one. It's not too expensive. So in summary here, I like to talk about the crew survival is one of the main drivers for vehicle design and mission architecture, and arguably should be perhaps one of the top considerations. You have to plan for worst case scenarios because safety is trying to prevent an accident and survivability is dealing with it when it happens. And I think you have to have a reasonable approach with both of those. What you have to consider, and this is something that I hadn't gone into in too much detail, but I've had a lot of crew that said, well, I don't want my system, I don't want a survival system to interfere with my nominal operation. And I would talk to shuttle crews, and about a quarter of the pilot commanders who are actually flying the vehicle with a joystick actually would take their gloves off because they felt they had better control. So this is an area that has to be taken into consideration, is if you're not wearing your gloves, the chances of you getting them on in an off-nominal event is very likely. So you always have to take into consideration what is the effect of the survival system on nominal operations. Because a nominal operation happens every time. An off-nominal operation, if you're lucky, is only going to happen 1 every 100 times or 1 every 500 times. So if you're impairing crew performance with your survival system, you have to take that into consideration. There are a lot of advanced technologies that are being incorporated now, and interestingly enough, NASA has been extensively involved with the high-performance race car industry because, as you all probably know, they have managed to create survivable mishaps with over 100 G impacts, where previously those were felt to be fatal and non-survivable. So we're heavily exploiting advances in other areas of transportation, particularly when they have, you know, high-speed crashes. It's always better to have crew survival designed into the vehicle before it's built, as opposed to trying to fix it afterwards. So with that, here's my contact info. If you all have any questions, please feel free to contact me. I have much more material I could go over in length if you're interested. Thank you very much.
Thanks, John. Would you be okay to answer a couple of quick questions if anyone has any?
Sure.
Does anyone have any questions you'd like to ask them? Andrew, maybe shout. Someone's got his hand up. He's going to ask him to shout loudly.
Okay, Mark, thanks very much for your talk. It's really interesting. Quick question about the new Orion suits for the Artemis missions. Looks like they're taking into account a lot of things that you said, but some of the stats are going to survive for 6 days in an environment potentially in a lower orbit. Does that take into account thermal protection and everything? So that's surviving effectively in an unpressurized in that period of time?
Okay, so I'm not sure I completely heard it, but I thought I heard the word Artemis mission and 6 days.
Yes, the Orion suits we were asking about and their survivability in them.
The Orion crew survival suit sounds like it's taken.
Okay, so the Orion crew survival suits are going to be, so Orion is the NASA program, and it's going to use either the Modified Advanced Crew Escape Suit or some rendition of that, and the goal is to survive for 6 days. You know what? It's going to suck. No, I mean seriously. So I'm not sure if the crew will be for the space shuttle era suits. They would wear, you know, it's called a maximum absorbency garment, but basically it's an adult diaper. Okay, so could you survive in a depressurized environment for 6 days? You can, but you're going to need some water. Now, the David Clark suit has a suit port, and you could stick a straw in it. We actually we use that exact same suit for the Red Bull jump. And Felix, he drank on his way up several liters of water through that suit port. So you can drink water in a suit that's fully pressurized without a problem. The downside is you have to get rid of it, and so you either are going to use a maximum absorbency garment, which will absorb most of that, but you'll certainly have one hell of a diaper rash after 6 days. Or you can just pee in the suit and let the suit absorb it. It's not going to come back to your head because you've got a neck dam that prevents that. So you won't necessarily smell it, but you'll certainly feel it. It's doable, but it's a severe situation.
Thank you. Are there plans for these suits for launch and re-entry, including gloves, helmets, so fully kitted, but not pressurized?
So I'm not sure I heard the question right.
So we're asking, are they planning on wearing the suits on re-entry, but having them fully kitted up, so with gloves on and helmets, but not necessarily pressurized?
Yeah, that's a great question. So in general, in a launch entry survival suit or an escape suit is flown depressurized, but is in a pressurized, ready-to-go configuration. Now, What that means is that you have your gloves on, you have your helmet on, and you have the visor open, but you can bring it down. They're now designing a visor that will come down automatically in a depressurized scenario so that if you were unconscious, it will still come down. They will wear the suit in its unpressurized configuration because it's just, generally it's easier that way. You have better dexterity and tactile feel. So all the, even the U-2s and the SR-71 pilots, who are flying, 8-hour missions, would fly in a fully configured pressure suit, but it's not pressurized. So, and there's quite a few reasons. One of them is that the suits generally operate, if they're operating at a low pressure, say 3.5 psi pressure, they have to have 100% oxygen to have a viable atmosphere. And the real problem we faced, even in the Red Bull program, was that we had to vent that oxygen. You couldn't vent it in the capsule because then you get 100% oxygen in the capsule. So you end up going to an open loop system, which means one breath in, one breath out, and that's very consuming for consumables. If you're surviving off oxygen inside the spacecraft supply where you've got more available, that's fine. But if you're on 100% oxygen, you've got to vent that atmosphere at some point because it's a potential fire hazard. So the bottom line is that generally fly in the survival suit or the escape suit unpressurized, but in a readily configured for pressurization. The Columbia crew, we had several problems there. 3 crew members didn't have their gloves on, and during the vehicle breakup, they started to move around, and their gloves were lost. And one didn't have his helmet on, or maybe it was 2. So, and none of them had their visors down. So the problem is, as the vehicle started to lose pressure, none of them put their visor down. If they had, there was potential that might have helped keep them alive to a lower altitude. But they were all exposed very rapidly to the vacuum of space and suffered the damage to their lungs. So anyway, I hope that answers the question. If not, feel free to write me and we can go into it further.
That's great. Thank you very much.
Veronica?
What's your take on commercial spacesuits like SpaceX or Final Frontier developments? What do you think is their perspective?
So I follow that very closely. I've worked as a consultant for SpaceX, and I was involved in their first human vacuum chamber test. So I'm very familiar with the SpaceX spacesuit, and I follow Final Frontier Design's progress. Right now, I think their main customer is going to be a balloon stratospheric project that is through Zero to Infinity, which is based out in Spain. So I think the more the merrier. We need a lot of spacesuit development and new idea. Final Frontier Design has developed a very robust glove flexibility system because one of their designers came from the Russian spacesuit company Zvezda. I was shocked that SpaceX was going to develop their own suit on their own, but their attitude is they don't want to deal with other suppliers. So they on their own develop their own suit. But both of those suits are internal survival only. They don't have the thermal protection to survive in deep space, like an escape suit does. But they're very good teams that are working on it. They test them extensively. One of the things that's I thought was absolutely brilliant was that their gloves don't come off. So they can never lose their gloves. If they want to use their hands, they have a little zipper. Can you see me on the video?
Just
is my video showing up?
if you stop sharing your screen, we'll be able to see you a little bit better, I think.
Okay, let me see if that Okay. So they have the glove and the suit connected, and they have a little zipper here, and they can take their hand out of the zipper, but the glove never comes off. So one of the things I've been super impressed with is the novelty of, hey, we don't ever want to lose the gloves. And what better way than it's always part of the suit. So they can take their hand out and use their hands to do stuff, but they never lose their glove. And if they have a depressurization event, they'll have to pull the glove back on. It's kind of like a skiing glove that's permanently part of your suit ensemble. So I'm very impressed with the novel developments that the commercial space companies are doing.
Any other questions, or are we? Ronnie's got
So all of the high altitude jump records so far being set in a pressurized suit with Eustace in Finn's bunk cabinet. What do you think physiologically would be the limit for the highest unpressurized jump?
Woo! Oh boy, that's a tough question. The highest unpressurized jump. You know, so first of all, you have to do things to prepare for that. So unpressurized means that you have to deliver oxygen at a viable amount, and so you would require positive pressure ventilation, systems. Which, have any of you ever done that? Like, I think Kinetic still does altitude chamber tests. It's very uncomfortable, and because what happens is the gas comes in, fully expands your lungs, and you have to forcibly exhale to get it out. So pressure suits are pressurized oxygen systems are required above 35,000, 40,000 feet. If you don't do that, you can't provide a viable enough gas composition. We are flying those systems now with, and it was actually developed in the UK. It's called assisted positive pressure ventilation. So there's it's called a jerkin. It's a chest garment that goes around, and it actually provides the compressive force so you can exhale against this pressurized gas. Those systems are flown in the US and other aircraft, but I know the F-22 has it. It's called Combat Edge. And they will fly routinely in the 50, 60,000 foot range, and they don't have a pressure suit. But they don't stay up there super long. So anyway, could you do a high altitude jump without a pressure suit? Yeah, but I think you'd probably be around 50,000, 60,000 maybe at the max. You'd have to get out of that ebulism region, which is, around 63,000, probably down to 55,000 feet, pretty fast. So it's doable. There's been certain groups that have been interested in doing that. I know they've done high altitude bailouts from 45,000 feet. And there's aircraft that can fly and that have bailout capabilities that go into the 50, 60,000 feet. The Gulfstream 5, 6, and 7 can go. They can fly that high. To depressurize, what do you have to do? You have to pre-breathe oxygen to get rid of the nitrogen stores, because you're going to be exposed to that ambient pressure. So one of the big problems is you have to do an extensive pre-breathe that's many hours long if you're going to go without a pressure suit. It's a great question. Believe it or not, there's a lot of people that have been asking that and trying to push the envelope. But we're in a very unusual area there. For the other thing that happens, so I have a colleague of mine, Ulf Baldin, who was a Swedish flight surgeon. He was doing high altitude exposures at 55,000 feet with an oxygen system. And what he said is the first thing he noticed is that he got grit in his eyes, which is essentially bubbles forming on his eyes. And so you have to have something that, keeps your eyes protected, because those bubbles can be irritating. So there's a lot of things that we don't put people in that environment very often. And when we do, we learn a lot. But great questions. If you want to try a project, let me know. I'll be happy to help you out.
Interesting. I think that may be everything for the moment. A bit of end of the day fatigue probably kicking in here. I'd just like to say thanks for a fascinating talk, John. Hopefully you weren't up too early to dial in with us. I really
No, I'm not. It's only 9 a.m. here, so it's a good hour for me. I'm bright-eyed. Well, thanks for your questions. If you have any more interests, let me know. I've got a lot of reference material. I've got a huge file. I'm actually in the process of writing a book chapter on crew escape, so it's kind of an area I've been very interested in. And actually, we still have projects ongoing right now. So the future is very bright for y'all. For me, I'm really honored to be able to talk to y'all, because to me, my role now is to pass the torch. And one of you, I'm sure, will walk on Mars.
Sure, if you would like to. Okay, thanks a lot, John. I appreciate it. I'll pass on any of his contact details who may want to get in touch with you about anything.
Okie dokie, great. Nice chatting.
You too. Bye.
See you.
Just for the admin, guys, roll paper tomorrow, get training, guys know where we need to be. I have great fun at the boarding passage. Now, hopefully, you know the boarding passage. We're trying to think about night in that park off for tomorrow. So, if you've got sense of you get one, will you see anybody before you arrive at the airport? Send me a message if you haven't got somebody getting sorted out, because I will go through security before everyone else can try and get the people tomorrow as well. See you all tomorrow. No, I spent 5 hours trying to get all of your details on, like, because the system kept breaking and not working, and I have to phone someone, wait the whole for an hour and then talk to somebody on the phone for all of your passport details. It's not a problem, I gave them like lunch in the end, but I was...
Then I was like, and then I written the email and then realized that it says like, as it appeared in my passport.
It's actually been fine. I got it all in the end, but the website was rubbish and I spent so long trying to do it. But yours was fine. I realised you made a mistake, so I was corrected that. I just wanted to make sure.
And I have to check my PR as well, because I am living in my PR. So I have to check. Biometric was yesterday.
The Mexicans need a visa to get to Germany. As long as you don't need a visa to get to Germany,
Okay, yeah. It's upset to get into the UK, but they tell me that every time I leave the country, I have to take something to get into it.
By all means, take that, yes. Visas and things are not my area, so make sure you have everything you need to go and come back.
Yeah, I'm sure I want to be stuck there.
No, not at all. You'll be in limbo and Heathrow, you don't want that. So. I'll see you tomorrow. The fun part then, guys,
Oh my god, she's like. Probably got you off. People willing to do that stuff, though. There's always people. So because the historical, well, that's part of the interest. So what hasn't been answered is historical efficiency can give them oxygen, which covers the altitude of the aircraft. So they might not produce
yeah, exactly. So apparently,
is it acceptable?
Yeah. There's no up too early, too late.
That's not in the end. That's neither what. And so, just a kind of could you, so what we haven't looked at is actually fresh breathing for altitude.
That is, I've got everyone,
chest pressure.
like, between.
Does that just give enough to prevent?
So the overall system pressure,
So there'll be
all around the
box.
is different.
It'll just be
said not the issue of these pressurized suits is 22.5 feet, and they've only got a brief period where they're exposed to 50,000 feet. Operating for a long period of time.
Sometimes there's always the traits of
But if you're talking about doing a jump altitude, you've got to get there. So it'll take you a long time.
I guess it depends how you get in. If you get near a pressurized capsule,
And then depressurise the jump.
that's more than
You need to be, so basically you need to play like G6 or G7, and then depressurize the platform.
Well, you have like say the moon with pressurized capsule, yes, that you can put in there. Because yeah, long like say hours or something like that.
that's a good way of leading to
Eventually